So just the same, I will show you the slides. What are the main concepts that we're going to be covering in this chapter? And then we can do some examples based on the textbook and some examples I have here. All right. Now is when we're going to start applying more of this whole idea behind dimensions, units, vectors a little bit, but let's see. So the main topics in this chapter are to introduce the idea of position, distance, and displacement. They are not the same. Position is, and you kind of already see it, you see when you have those coordinate points in the X and Y axis, that's a position. For example, 4,3. That's a position in the X and Y plane. The vector will be, well, 4, 3, 5. Magnitude, right? So that could be the distance. And the displacement is the vector and is defined as the final position minus the initial position. So there can be instances where you're, depending on your final and initial positions, you may have a negative displacement because it's a vector, but you never have negative distances. Distance is always at least 0. Okay, it cannot be less than 0. And it's only 0 if you don't move. Okay? Then you have speed and velocity. Right? And they are different. Right? Speed is basically the magnitude, the scalar quantity. And speed is related to distance, while velocity is related to displacement. Then we talk a little bit about instantaneous velocity. Then we define acceleration, motion, and we're going to assume constant acceleration because we are going to use, or we're going to be heading towards the main application, which is falling objects. And what's acceleration of a falling object? Gravity. Okay? So that's the main idea. Those are the main ideas. There's more, of course, in between of chapter 2. And then later in chapter 3, we're going to combine because we're going to be doing not just one direction, but 2 directions. Okay? In chapter 2, we only deal either with the X or the Y independently. So that's a good example there, right? You see at the beginning in there, the body is at position 1. But then it moves forward and then backwards. After 4 seconds, the particle is at position -1. Now I'm going to show you with this what's the difference between distance and displacement. So position is where it started, this point and this point. The distance is all this that it traveled. So from 1 to 4, that's 3 meters, 4 meters. So 5 plus 3, 8 meters. So the body moved 8 meters. 3 to the right, 5 to the left. That will be your distance. But what about the displacement? For the displacement, you want to know what's the initial position, which is 1, and the final position, which is -1. So your displacement is -1 minus 1, which is -2. So your displacement is 2 to the left. And that makes sense. Look, 2 to the left. So for displacement, you care about the position, the initial and the final position. And it can be negative. For the distance, I care about the whole trajectory. Okay? That's why we say that distance is a scalar, displacement is a vector. Because I can also say that my displacement is -2 or 2 in the negative x direction. You see, that is already, that's a vector there. And then we can use how long it took, right? For the distance of 8 meters, it took 4 seconds. So the speed is 8 divided by 4, 2 meters per second. What about the velocity? The velocity is displacement over time. My displacement was -2. The total time was 4. So -2 divided by 4 is -0.5. So my velocity is -0.5 meters per second. You see the difference there between velocity and speed? And by the way, that velocity is -0.5 meters per second to the left. You see? So that's why we need to understand, that's why it's important to understand the difference between both position, distance, and displacement. Okay? For one dimension, like I just showed you, we only care about either the x-axis or the y-axis. So we always use the origin as the reference point, and from there you have initial, final, and the arrowhead indicates, if it's to the right, positive direction. All right. So what do we have there? It says that the distance is the total length. Yeah. So if you go from your friend's house to the grocery store, this is all the distance you travel. 2.1 miles plus 4.3, that's 6.4 miles. That's all the distance. Now it says here that you drive from your house to the grocery, and then you go to your friend's house. No, then if you go back, okay, yeah. If you go from your house to the grocery store and then you go back, that's 4.3 plus 4.3, that's 8.6. But guess what? Look, you are in your house, right? You go to the grocery store and then you go back to your house. The distance is 8.6, but the displacement is 0. Do you understand why the displacement is 0?
Yeah.
Why is it 0?
Because the starting and the ending point are the same.
Yeah. Yeah, so if you go in a loop, your displacement is 0. Because your starting and final position are the same. Yeah, so here they give you an example, right? Displacement is a change in position. So if you go from your friend's, from your house to the grocery store, and then to your friend's house, again, it doesn't matter. Your initial position was your house. Your final position was your friend's house. So your displacement is -2.1 because you're going towards the left. Just like in the example I did at the beginning. Okay? The displacement is negative because it's towards the left. The distance, though, 4.3 plus 4.3, that's 8.6, plus 2.1, that's 10.7. So you travel a distance of 10.7 miles, but your displacement is -2.1 because, again, in displacement, you only care about the initial and final positions. So that's why once we have that, we can define average speed and average velocity. Like I said, speed is related to distance and time. Okay, so the average speed is distance traveled over time. Okay. What about displacement? Or what about velocity? Velocity is displacement over time. So if you go back and forth, right, you can sprint and then you can walk back to the initial position. Your average velocity is just 0 because the displacement is 0. Okay? Does that make sense? Yeah. Now, we can visualize this with graphs. Like, for example, this example we had at the beginning, right? You started at 1. After 4 seconds, you finish at -1. So you can do a graphical interpretation. you start a position here. After 4 seconds, right? Or after 2 seconds, sorry, you are in position 4. After 2 more seconds, you are in position -1. So you go to the right, so you increase your position, but then you decrease it until you are in a -1 position. Okay, sometimes doing graphs like this help you. And you know why they help you? At least to analyze the velocity. Okay, because the velocity is the rate of change of displacement. And displacement is related to velocity. So I could say that the velocity in the first 2 seconds was positive, and the velocity in the last 2 seconds was negative. You know how I know that? Let's see if you guys remember this. Let's see. So when you have a curve, right? If you have a function like that, so in the slide, they show you this, right? One, 4, and then -1. 2 seconds, and that's in 4 seconds here. Time in seconds. Position X in meters. Okay. So velocity is delta X over delta T. Displacement over time. That's how you label it. Using symbol, using math. Meters per second, SI units, meter seconds. Delta S over delta T is a slope of a line, right? Or it's just your slope of a line that can be tangent to this curve. So my curve is like this, right? So if I draw a line, my line is going to have this orientation. So any line like that has a positive slope, meaning positive velocity. And between 2 and 4 seconds, my line will be like this. This has negative slope, which is a negative velocity. So that's why these graphs are useful. The other reason they are useful is for the instantaneous velocity. What is the instantaneous velocity? It's basically the velocity at a given second, not in between 2 and 4 or 0 and 2. It's the velocity at 1, the velocity at 3. And for that, so for example, if you have this, if you want the instantaneous velocity at this point, you draw a tangent. The slope of this tangent curve, the slope, that will be the instantaneous velocity. And we don't go much into that because to find that slope, you have to use what we know in math as a derivative. And a derivative is a calculus concept that we don't have to worry about now. So that's why we Okay, let me answer this question about the lab in a bit, okay? Sorry, there was a question here. So that's why we only care about the average. The average velocity is the velocity between certain displacement and certain time. For example, between 2 and 4 or between 0 and 2, right? If they want you to find the average velocity between 0 and 2, we can do that. Yeah, we have the values. The position at 0 is 1. The position at 2 is 4. So if I want to find the velocity between 0 and 2 seconds, that's my displacement from 1 to 4, 4 minus 1 over the elapsed time, which is 2. 3 over 2, 1.5. Yeah, positive. Okay? That would be my velocity. And I showed you before how to find the speed, right? But for now, we're focusing on the velocity because velocity, again, is displacement over time. So that's how we label it. All right? Okay. So graphing it like that helps. Oh, yeah, so here it is, right? So, like I said, the instantaneous velocity is when the time difference is basically 0, is the limit. That limit is basically the derivative of position with respect of time. All right. And again, we don't really worry so much about that because that's a calculus concept. But if you want to see it, it's also here. That's what I was showing you, right? For the average velocity, you can use a line like this between 0 and 2 seconds there. You can find the final position, initial position. You can find the average velocity. For the instantaneous velocity, you draw a tangent line because you want the velocity in a particular time, in an exact value of time, not between a range of values of time, like between 0 and 2, or 2 and 3, or 2 and 5, okay? So using the slopes allows you to do, so that's kind of what I show you. The slope tells you the average velocity between times. And the sign of the slope, and the thing is, right? Remember, when you have a line like this line has a negative slope, so the velocity is negative. This line also has a negative slope, so the average velocity is also negative. This one here, the one that is tangent, is a positive one. So it makes sense. Look, the body, the displacement is decreasing, but then here it starts increasing again because the displacement starts to increase. The velocity also goes from negative to positive. Okay? So analyzing the velocity and this graphical analysis that you can do allows you to understand at least the direction, because the positive means that you're going to the right, negative means that you're going to the left, like you saw here. Right? The reason the velocity between 0 and 2 is positive is because the body is moving towards the right. As soon as you start moving towards the left, your velocity is negative. Okay? So then we can, so now we have defined displacement, velocity, average velocity, instantaneous velocity. We can also define acceleration. Okay? So if velocity is displacement over time, acceleration is change on velocity over change on time. So average acceleration or acceleration is the rate of change of velocity, right? And eventually, in many applications, we can just say that acceleration is the rate of change of speed, right? If the body is just moving to the right, and that's the thing though, right? Many applications, objects are just moving to the right or just up or just down. So the velocity and the speed, they match because they're just going in one direction. When you have those changes on directions, that's when they change. But if you have a body going in just one direction, at least for magnitude wise, they match speed and velocity and acceleration. Okay. So that's my acceleration there. The thing about acceleration is this. You can also do the graphical analysis. For velocity, we do position over time. For acceleration, we graph velocity versus time. So let's see. And let's give you a simple scenario, right? Velocity versus time. Time in seconds, velocity meters per second. So let's just do a simple case. A body that starts from rest. So let's do this. If they tell you that a body starts from rest, then the initial velocity is 0. Okay? So if you start from rest and then you increase your velocity in some given time, let's call it V final, V initial, which is 0, and then in some time, let's call it T. This line also has a slope over this, right? Y over X. So the slope in a velocity versus time is the acceleration. The acceleration here is V final minus V initial over T minus T final minus T initial. But V initial and T initial are 0. So acceleration is V final over time. That's a simple case. If V initial and V final are non-zero, right? Then in general, we get our famous equation V final is equal to V initial plus acceleration delta T. Delta T is change on time. So that is a famous kinematic equation. It relates the final velocity, initial velocity, and the acceleration. And delta T is T final minus T, which is normally the elapsed time or time. Okay. Now, I'm assuming that the body is accelerating, it's gaining velocity, but you know that you can brake, you can slow down. That's also an acceleration. So how do we quantify? It's the same. You can have positive acceleration, you can have negative acceleration. Negative acceleration will just be this. This will give me a negative acceleration. So negative slope. Negative acceleration. And the thing is, I can use the same equation, but I'm going to make it general now. Here. So, in general now, for positive and negative acceleration. So, speeding up or down. Your final velocity is your initial velocity plus or minus acceleration time. This is, when you use minus, when you're slowing down. When you use positive, when you are accelerating, when you're speeding up. Okay? So that is your equation. That is when there is acceleration. If there is no acceleration, then your velocity doesn't change. So then the equation is just distance equals to, or displacement is velocity times time. But in most of the real life scenarios, we have acceleration, right? So there you have it. All right. So that's what we have also in the slides. We have our definition of acceleration with a graph. And let's show you the graph I just did on the board. You can find it also here. There. Okay. For a constant acceleration, if the body is spinning up, that's the case. And look how they show you the average velocity. If you have acceleration, if the acceleration is constant, the average velocity is that. But hey, we know what the average acceleration is also. I'm going to leave that in there so you guys can see it. But I'm going to use that to show you another equation that I want you guys to also write down and never forget. Is we use it sometimes. Okay. So you see what you have on the slide, right? And you have this equation already. Now, your average velocity is defined like this for constant acceleration. So that's another assumption that we do. And for free fall, for example, right? For free fall, it's okay. For free fall, or for anybody that has constant acceleration, that's true. But you just saw in the slide that the average is the half of V final plus V initial. So guys, besides this equation, you have another equation here. Displacement over time is 1/2 of V final plus V initial. Very important equation as well. But be careful though. This particular equation only works for constant acceleration, which is the cases that we're going to be doing in the course. So it's fine. Okay, so just to work. And you know the thing about this is that I can combine this equation and that equation. And I get another equation. All right. This is a definition of acceleration. And this is the definition of average velocity. Using the equation of average velocity and the definition of average velocity for constant acceleration, I get this equation. Okay. By the way, guys, in terms of notation, I like to use VI and VF, but in the textbook and in some, you know, if you go online, sometimes they use V naught as initial velocity. So, so just keep that in mind. Both can be used as initial. All right. Anyway, let's combine these two. How? Well, delta x, delta t, 1/2, v final, v initial. But wait, I know what v final is. So let's assume the body is speeding up, and then we can generalize. And you see what equation we're gonna get. So let's write these two here. So if we assume positive acceleration, v final is v initial plus at. Let's keep it simple, just like that. And then that one is delta x over delta t equals to 1/2 v final plus v initial. So to combine these two, I'm just gonna write VF here. So delta x over delta t is equal to 1/2 v initial plus at plus v initial. Delta x over delta t, vi, 1/2 2 vi plus at. All right, so I can multiply here and look what I get. Delta x is 2 divided by 2, 1. Vi delta t plus 1/2 acceleration t delta t squared. There you have it. Another equation. It's nice when you can prove these things instead of just writing them down. So I just show you how to get the equation for position or displacement. And eventually we're gonna say that's the equation for distance. Okay. For distance, we use the same. Distance is speed times time, or initial speed times time plus 1/2 at squared. Now, in general, what do we have? In general, we have that delta x is v initial times time plus or minus 1/2 acceleration time squared. Why plus or minus? Because you can be slowing down. If you're slowing down, you have to use negative, right? And then we have this, right? Well, we have this one here. 1, 2, 3. Okay. So those are what we call the equations of motion, or the equations of one-dimensional kinematics. All right. The other equation is, if you wanna, like, you could combine this equation and that equation. That's a bit longer, but basically you solve for time. If you solve for time, you get an extra equation, which looks like this. V final square is equal to V initial square plus or minus 2a delta x. So, guys, you have 1, 2, 3, 4 equations of motion. Those equations you have to memorize, but you have to have it in a formula sheet. All right, those are gonna be in the formula sheet. But if you decide to write your own, you should always have these 4 equations, right? Let's put here the general one: V final, V initial, plus or minus 2. A delta t. All right. And then you have this one. Okay. Any questions? I mean, I'm just showing you the equations that we're going to be using. All right. For constant acceleration, these are the equations of motion. All right. So the strategy for the problems at the end of the day is to know which variables you are given and which values or which variables to solve for. All right. So yeah, let's actually do a few examples now. Let's see. Let's leave that in there. Okay. So there. So I'm gonna write the equations over there, and I'm gonna show you guys an example. All right. Okay. So for one-dimensional kinematics. We have the final, the initial, plus or minus AT. So we'll leave it like that. X equals to the initial times time, plus or minus 1/2 acceleration t squared. B final square is equal to B initial square, plus or minus as well, 2a x, and x over t equals to the average velocity or speed. Okay, that's how you're gonna find it in the equation sheet. So I'm gonna write it like that. And let's see. Example. It says you have a body moving with constant acceleration. So you have a mass moving to the right with constant acceleration, like that, of 4.50 meters per second squared. And after some time, so after some time, it reaches a velocity final of 12.5 meters per second. But if the initial velocity was 6.50 meters per second or 6.5 meters per second, what is the displacement? Okay. So you have a body with some acceleration. They don't tell you the, oh no, they tell you the initial now. The acceleration, and they give you the final velocity. To find the displacement, okay, so there are two equations where you have x, or three equations. For this one, you need time. For this one, you don't need time. For this one, you need time. So this equation here is a very nice equation. Because in that equation, you don't need time. So you have the final, you have initial, you have acceleration, you can solve for x. So now is the algebra, all right? So let's see. I'm gonna use b final square equals to b initial square. Is accelerating, so plus 2ax, where x is the displacement. B final is 12.5 square. B initial is 6.5 square plus 2 parentheses, that's multiplication, 4.50 times x. Okay, so we just have to solve for x. 12.5 squared, 6.5 squared, we're going to subtract those, so let's find the values first here. So 12.5 squared. Okay, so here, that's 156.25. That's 6.5 times 6.5. That's 42.25. Plus 2 times 4.50 is 9x. So this minus that divided by 9, right? What do you have to do? We subtract 156.25 minus 42.25. That's nice. That's 114. So this minus that is 114. That's equal to 9x. I divide by 9. And I get my value of x. 114 divided by 9. I get 12.6, 12.7. Yeah, 12.7. So that would be my value of x. So my displacement is 12.7 meters. All right, questions? Any questions about this? It can be the math, it can be the, in terms of units, everything is in SI units. We don't have to do any conversions. It's just knowing what equation, right?
Why is it 3 sig figs?
Because of this. 114, the final has to be that. 3. Oh wait, that's 6 plus 2, right? Oh well, but that was a whole number, that's why. So I left it as a whole number. Since I left it as a whole number, I end up rounding it like that. So 12.7, that's the answer I have in there. But if you decide to run it as 2 sig figs, what will be the final answer then?
13.
13. Yeah. So the way this works, you always want to get a margin of error. So normally it's like between 12 and 13 is the accepted, 12.5 and 13 is the accepted answer. All right? Yeah. Any other question?
So just to confirm, you would take any of those answers, like on a test or quiz?
The way we do it is we accept a range of answers. So if you run it to 13.5, that will be wrong. If you run it to 13, that will be correct. If you run it to 12.5, that's okay. It's within the range. So 12.7 is between the accepted values of range.
Thank you.
The way we do it in in Cengage is they give you a range of accepted values. Normally it's like 10% of the accepted value. So you're normally fine. Okay. Be careful when you, like for these problems, it's probably not a big issue, but sometimes when you round in between, that's when you can get answers that are a bit off the accepted value. So just be careful with that. But I have made the assignments. So you have, let's see, you have that range. So the accepted value here is, yeah, 12.7, 12.5. So, okay.
Wait, I still don't get why it's 12.7, not 13.
Because I rounded using the 114. So 114 has free sig figs, so I just kept that as free. But if you use the original, right, here is 2 and this is free. So if you go back all the way to this, right, this degree of precision, then your final answer will be 13. And by itself, that's 13. Okay?
Okay, thank you.
Yes, I use this. And sometimes it's better to use that because that gives you like 12.7 probably is a bit more precise than rounding to 13. But yeah, if you're gonna use the original values, that's 2 sig figs, that's 3 sig figs, then that's 2 sig figs. Okay.
A question on that. However, the question does include the 0. Like it says 6.50 and 12. So wouldn't we still do 3 sig figs?
Oh, if it's 6.50.
Yeah.
Like that.
Yes.
Like that. If it was like that, yes, that would be the answer, right?
Another question. In an exam, do we have to show our work for how we derive the units? Like in this question, we know it's meters for the final answer because it's displacement, but do we have to show it's because final velocity squared and initial velocity squared would have meter squared over like second squared, and you have to divide it by meters per second squared?
No. So in the exam, the work that you have to show has to be like this. All right. As long as you have everything on the same units, meters per second, and meters per second squared, then, all right. And that's what they also show you when you guys go, if you guys already have access to the book, that's how they show you the examples, all right? You only have to worry about units if you are given a question, and I'm gonna look for one now, where you have different units. So let's see, I think there's one that I added here. That's free fall. That's okay. I can make one up. So I know there's a question on an exam where they combine. Okay. So in here, yeah, like you said, we didn't have to worry about the units because everything was in meters per second squared. So the final answer is in meters. So you don't have to worry about units or showing how you get those units. But let's do an example where you have to do that. Okay. So can I erase this? Yeah, okay. So now let's give you an example like an airplane again. You have, say, an airplane that is landing on a straight road, right? It lands at a speed, so now no velocity, one with speed, at a speed of, say, 240 kilometers per hour. a bit too much, but initial. And it travels a distance d and it stops here until it stops there. All right. If the airplane stops after, okay, what will be a real value of time after 3 minutes? That might mean not, yeah, 4 minutes. After 4 minutes, calculate the distance traveled. The distance and acceleration. All right, guys, I'm gonna let you guys do this. Let's see how you do it. It's a nice problem. I remember doing giving that in the exam. All right, so the airplane lands with that initial speed and it stops after 4 minutes. Find the distance and acceleration of the airplane. While you guys are doing that, first quiz is on Thursday. All right, chapters 1 and whatever we do, well, we're gonna be doing probably most of chapter 2 between today and tomorrow. So the way the quiz is gonna work is on Thursday. I don't think I will be on campus. I think I'll just be at home that day. So I will do a class between 6 and 8-ish. And then I will open the quiz and you guys can work on it on the last 25 minutes, 30 minutes of class. Okay. If you need an extension or if you have accommodations, please, I got a couple of emails today. So I will take that into consideration. And also, as I said, I might use lockdown browser. So if you have issues with that, please let me know. I'll be on the Zoom. I will keep the Zoom open. So if you have issues, we can figure it out. Okay. So just make sure you show up, you come and you stay till the end on that day. Yeah, Thursday at the end of the class. Quiz number 2 might be asynchronous. So normally what I do for quiz number 2, and I've done this in physics 2, is I do the class like normal, and then I let you guys work on the quiz for 24 hours. You have like an online, but it's a bit more challenging, but you have notes and all that. So that might be next week. We'll see. Okay, what's the first step for this problem, guys? So what are you doing right now? What's the first thing you have to do?
I guess choose the right equation.
Yeah, but what about the values? You have kilometers per hour and you have minutes. So
yeah, convert it.
Yeah, so I didn't specify, make sure that the distance is in meters and the acceleration in meters per second square, okay? So if you convert it, how do you convert, we just did it today, right? How do you convert 240 kilometers per hour to meters per second?
We know that there's 1,000 meters in a kilometer and 60 seconds 60 times 60 seconds in a hour.
Yeah, and if you remember, and I'm pretty sure you have in your notes, this, right? Just multiply by that. So, all right. Anybody, what do you get for V initial in meters per second? Is that right? Is that what you got? You can run it to 67, right? Is that fine? And then 4 minutes. That? Okay, guys, so that was a conversion. What equation are you using or did you use?
I use VF equals VI plus AT.
Yeah, so that to get the acceleration. Very good. Okay, so to get the acceleration, we just use that. Let's do it here. To find acceleration. Oh yeah, what's the final?
0, it stopped, right?
Yeah, good. The final is 0. So 0, let's just put here the equation. The final, the initial, plus or minus AT. So the final, the initial is slowing down minus 8 times 240. Okay, what do you guys get for A? What do you get for acceleration? Point 28 meters per second square. Does that make sense? Yeah?
Is it negative?
Good. That's a good question. Magnitude-wise is that depending on the question, yes, your vector acceleration will be negative 0.28 meters per second square because it's slowing down or to the left. Good. Magnitude of the vector with a direction. Now, I asked you for the magnitude here, but yeah, both are valid answers. So, okay. And what will be the distance? How do you find the distance?
We can use all this and just plug it into another equation.
What equation? There's one that I will use if I were you. I wouldn't use this. I will use this. It's easier. I will use the average velocity equation. It's more simple. X over time, X over time, or if they ask you for the distance over time because it's just going to the right, even though it's slowing down, it's just moving in one direction. Distance over time is 1/2 of V final plus V initial. Distance over 240 equals to 1/2. V final is 0, V initial is 67. So 120 times 67, let's see. 8,040 meters. Around 8 kilometers. Makes sense. I mean, that's it. Yeah, maybe a bit too much, but I mean, I just made out those numbers. So there you are. How about that, guys? Questions about this example? So this is a good example with units, where you have to show the units that you have the right units and that the answers are in the units that you're being asked. Come on, guys, any questions?
So you said to use the distance formula, not distance formula, the average velocity formula for this, right?
Mhm.
Okay.
Try using the other one, see if you get the same. You should get the same.
Okay.
But as you do problems and problems, you know, you start knowing which equation is better to use, like to do things quicker in terms of the math. And this example actually gives you nice information, and that's why it's an advantage to find acceleration first, right? It's easier. So that's a typical example, by the way. Like I told you, right? Question part 1, part 2. There's a question in the book on questions where we have to go back to the graphical analysis. So I'm going to show you here. I'm going to open the book, and then let's discuss that. Guys, if you have issues with WebAssign, I already got an email today. My recommendation is you have to purchase Cengage through the library. So all of you guys are going to be coming tomorrow to campus. So come a little bit earlier and go to a library, because they are the ones who know how to do all this. All right. And if you're going to be doing, most of you are going to be doing physics too, you probably need a yearly one. So it's just a suggestion, all right? This question. Let's talk about this. Let's make this bigger. All right. So this is another classic equation of motion. I want to see how you guys think about this, all right? The answer there, great. Okay, let's just right here. So they give you a position. Everybody is looking at the question, right?
Yes.
Yep. So we have no. Oh yes. We have a position versus time graph, like I showed you in the slides, and they ask you to find the average velocity in the following intervals: 0 and 2. Okay, what's the answer for that? And how do you do it?
It would be 5 meters per second. That
Good.
would just be 10 over 2.
Yeah, 10 over 2, right? So you do position 10 minus position 0, that's delta x, divided by 2 minus 0, yeah? And that will be 5 meters per second. Is that clear for everybody?
Yeah.
Yeah? Now it's asking you between 0 and 4.
2.5.
Huh? How much?
I said 2.5.
I don't think so.
Oh no.
What do you do? So how do you get 2.5?
Oh, I think I was thinking of something else. My bad. I did like displacement or something.
What's the displacement between 0 and 4?
Oh, I don't know. I'm just confused at this point. Sorry. Give me a second.
Anybody else who wants to jump in? Nobody?
Can it be like average velocity from like the velocity of 0 to 2 and the velocity of 2 to 4?
No. Just
Average.
Is it
Look at
1.25?
yeah. You look at the position. Look at the position of 4 and the position at 0. What's the position at 4? Look at the graph, guys.
5.
5.
5. 5 minus 0 is 5. And what's the time? 4. What's 5 divided by 4? 1.25. Does that make sense? Who has questions? Come on. Let's see the chat.
Wait, because like the line is going down, do we subtract it from 5 or something? Or is it just like 5 over?
No, remember, for velocity, you only care about the final and initial positions.
Okay.
Yeah. But hey, wait a second though. Between 0 and 2, what was the average velocity?
5.
And between 0 and 4, we got 1.25. So why do you think it's less than before?
Because we're decreasing.
You're decreasing. That's why. So it is reducing. It's not negative yet. All right. But what about between 2 and 4? So now we're looking at this slope. So C, what's the answer for C?
3.75.
It's between 2 and 4. Be careful with the time.
Negative 2.5.
Yeah, negative 2.5. How do you get it? How do you get negative 2.5?
Honestly, I just looked at the graph and I found the slope, which would be the same as x over t is equal to the formula that you gave us, the fourth one.
Yeah. Yeah, you can use the slope. So you can use algebra. Yeah, good.
Professor,
Yeah,
wouldn't it just be the final minus initial divided by the time?
yeah. 5 minus 10 divided by 2. Yeah. 5 minus 10 is negative 5. Divided by 2 is negative 2.5. Let's see if I can do it here with this. So let's do it for so it's clear. For C. For C, should bring a mouse for this. Negative 5 minus, oh sorry, negative 5. 5, so positive 5 minus 10. That's initial position divided by 4 minus 2. 2. Negative 5 divided, so 5 minus 10, negative 5 divided by 2, negative 2.5. Is that clear? So that's the average velocity between 2 and 4 seconds. Is that clear, everyone?
Yes.
Yeah? Okay, so what about 4 and 7 now? What's the displacement between 4 and 7? 4 seconds and 7 seconds.
Professor, I can't see well on my screen. Is that at 7, is it -6 or -5?
-6. I will take it as -6.
Okay, thank you.
Yeah, -6. The line is very thick. That's why.
Would it be -1/3 meters per second?
Negative what?
-1/3?
-1 or -11? What's your final position?
Yeah, -11/3.
Okay, my battery is
Would
going.
be negative 3.6.
Yeah, -3.6. Yep, because you do -6, -5 divided by 3. That's -11/3. That's -3.6. Yeah.
Is it okay to leave it as -11/3 as
It's okay to leave it as a, yeah, that's okay. That's fine. Yeah. What about E? Between 0 and 8. That should be easy, guys. What's the average velocity?
0,
0. Is that clear? Why is it 0?
because you started and end at 0.
Questions, guys. So this is a classic question on motion as well. They give you a graph. You have to find average velocities. Let's use that graph. I'm gonna test you guys in this. Between 0 and 6, look at the graph, huh? What's the average speed? Not velocity. What's the average speed between 0 and 6? Be very careful. All right? That's it.
Would it be 20?
20, what's 20?
The speed.
No, you're close, though.
Oh, no, sorry, divided by, wait, yeah, so 10. Maybe I'm messing myself up.
Close, you're close. 20 is the distance, yes. What's the time between 0 and 6?
Oh, divided by 6, so 20
Yeah.
over 6. Okay, yeah, I got it.
Okay, is that clear? Who has questions about that? Come on, guys, be honest, because I can ask that question in the exam.
I don't get it.
You don't get it? Yeah, that's fine. So basically, you have to find the distance traveled between 0 and 6. So let's analyze line by line, okay? In this line, what's the distance traveled?
10.
In this line, how much did you move?
10.
10. All right. In this line, how much did you move?
5.
5. You leave it as positive because it's distance. 5. Did you move here?
No.
No, it's horizontal. You didn't move. You stay in the same position. Now here, how much did you move?
Another 5, positive still.
So what's the total distance?
20.
And what's the total time?
6.
There you are. Is that clear now?
Yes.
Yeah? Nice, right? So that's a nice problem there as well.
Wait, sorry, so the answer is 20 over 6 meters per second? Or
Yeah. So
Okay.
10 over 3, about 3.3 meters per second.
But then you said when we do 0 to 8 seconds, it's 0?
Okay, so that was the question here, right? The velocity. The velocity between 0 and 8 is 0. Why is it 0 though? What's the difference between velocity and speed?
You're changing direction versus direction is not accounted for. So like in velocity, if you go east and then west or something, it cancels out. But in speed, they don't account for that. So it's always going to be positive.
Yeah, pretty much. In velocity, if you think about it, you are going in a loop. You're going up, down, but then you end up going to 0 again. You didn't move. Your displacement was 0. So your velocity is 0. Does that make sense? Come on, guys. Make sense or not?
Yeah.
Yeah?
So wait, the 16, no, 20 over 6, that is the distance traveled
So
and the
this is
speed.
none of this is this, by the way. This
Oh.
is this extra, all right? That's extra. This 20 is a distance travel between 0 and 6 seconds. All right? So if you look at the distance, not the displacement between 0 and 6, 10 plus 5 plus another 5, that's 20. And the 6 seconds, so that's the average speed. This question is about average velocity. I just gave you this extra because I want to make sure that you understand both. There's a difference between average velocity and average speed. I explained you in class, but with a problem like this, I hope that is more clear. And by the way, it's on the assignment, so you can do it after class. Different numbers, but practice it. All right?
Okay.
Sorry, just to clarify, you said speed was distance over time, and velocity is the change in speed over the change in time.
No, velocity is displacement over time. Okay?
Okay.
Let's do this. I want you guys to do this. I'll change the number. It's another one. So you have the problem in front of you. Oh my God, I need my battery. So when I go and get my charger, I want you guys to do this. So it's asking you to find the acceleration. Yeah, easy. You can do that. We're about to finish today, but I want you guys to do that, okay? So charger for this. Okay, good. All right, I think I give you enough time for this, right? So what do you get for the acceleration?
I got 8.39 meters per second per second.
So seconds. How do you do it?
So it's going to be the final minus initial, the initial 0, because it said, yeah, from 0. And then the finals, 21.4. And then over time. So that's just 21.4 divided by 2.55.
Yeah, so I like to use this sometimes. It's easier to just show you here. So yeah, B final is 21.4 meters per second. B initial is 0 meters per second. Time is 2.55. So yeah, if you organize your values like that, then you know B final is B initial plus AT. 21.4 equals to 0 plus 8 times 2.55. So like you said, what do you get for acceleration? 3 point what? No, that's
8.39.
meters per second squared. All right. So you have to use that for part B.
Quick question, Professor.
Yeah.
So in this, the significant value matters because 3 and 3 both have 3 and 3. So we can put the answer in 3 significant. That's
Yeah,
fine.
you can put it like that. And it will, for example, in this, if you put 8.40, it will mark it as correct as well.
Okay.
Yeah. For part B, you have to find a time between those two speeds.
That's gonna be 4.1. No, sorry, 4.20.
Yeah, so you will use, it's a constant acceleration. So how do you do it? You use the same equation, right?
Yeah, so I just did the 21.4 minus 10.7, and then I used the acceleration from last time. I mean, I just rearranged the equation, so I switched out t from the bottom to make it equal to t, and then a is underneath now, so I divided it by 2.55, and then that's what I got. I rounded it to 4.20.
Let's see. So 21.4 minus 10.7. Okay, divide by 8.39. Is that what you got, 1.28?
Oh yeah, that's right. I just plugged in the wrong number for one of them, but yeah, sorry. I mixed up the time and the acceleration, but yeah, that's right.
If you guys have questions, I put here the procedure. It's just using the first equation. It's not that bad. All right. That's what we did.
Wait, could I see B again?
Yeah. Let me make it bigger. Better like that?
Yeah, I can see it now.
Yep. That's part A. Part B. So use the same equation, use this equation.